Now we have our encoder output, which is this dimensional, and now we have to pass this into the decoder side and see. This will be used for the cross attention in the decoder side. I will give a quick overview of what was happening in the encoder side. So in encoder side, for each query we produce the corresponding delta x delta y's using a linear layer and sampled in each of the feature map the corresponding points. In our case, here we had 4, and here we have 3 and 3. In our case we had 4 and 4 and 2 across 8 different heads. And finally we had a self attention. We have a linear layer producing the corresponding attention weights for each of these points and aggregate them and finally get the output. So that output is this output, and this will be correspondingly passed to the n number of encoder layers, and this will be the final output of the last encoder layer. And now this will be used for the cross extension in the decoder layer. So initially what we have here as an input to the decoder is we have the positional embedding, which is a learnable position embedding, and number of queries is 300, and we have also have an input query which is also 300. So we have two matrices, uh, this positional embedding and input query. The positional building will be added to all the hidden dimensions, like say uh, after we pass through the first self. Yeah, I can show how the positional embedding will be used, and it's learnable. So the first point you need to understand here is this input query uh, is actually v plus positional embedding is actually passed through a multi-head at self-attention. So the initial layer is similar to what we have in Detr, which is similar to a multi-head attention. And here why we are okay in using multi-head attention is because our query sequence length is smaller. It's 300. It's in encoder side it was 23890, so here it's much smaller. So we are fine with using multi-head attention for the initial self-attention part. So that is done. So you can see this is the key, this is the query, and this is the value matrix. So the output of this hidden self-attention will be used as an input to the next cross attention layer. So if you remember, in encoder side we actually had xy's as the center of the grid map, and here the query, each query doesn't, like from the encoder side, doesn't correspond to a xy point or as a grid map, so we cannot take sender as a query. So what we do is we have a neural network, a feed forward layer that's predicting us the two embeddings that we need to use. So we have, if you look into here, a decoder reference point layer. So it's a similar layer that produces it two dimension, and then we have to expand it along the badge and along the channel. So this will be the reference point for each of the queries, and this this is a learnable reference point. So in encoder side we were taking it as the center of the points, but this is actually learnable reference points. And then so this is a reference point. So this reference point will be, we'll be looking into the queries from this reference point. But before that, in the multi-head self-attentions, we need to get the delta x delta y's from the sampling offset and the sampling attention layer. So we can see what happens there. So here as you see, we have the sampling offset layer, and so here is the sampling offset layer, which produces number of heads, number of levels, number of points, and 2, and the same for the attention layer. So this is exactly similar to what was happening in the encoder. And so this sampling heads takes the hidden dimension, which was the previous self attentions added to the positional embedding, and they took it and they take it and produce the corresponding sampling offsets, and we also have to normalize the sampling offsets, uh, like divide by the corresponding feature map size to be in the same dimension as that of the other. And then another thing that we need to do is, here the attention weights are also coming from the hidden dimension, same hidden dimension there. So these two will be the attention weights and the hidden states. And now uh, we can add uh, so the attention has to be softmaxes, which is the normal thing that you do, and then we add the reference points and sampling offset, and we get this much positions. So these are the positions that we need to look into the encoder side, and what happens in encoder side is the same. So these many points we need to look into. So for across 8 batch, across 4 levels, 4 points. Yeah, so for 4 levels we have to look into 4 points, and we have the corresponding xy's of the points, and these are learnable xy's and learnable delta x's, delta y's. And now we see the same, I just copy pasted the same code from encoder side. So what is happening here is also the same. So we have the encoder feature map, which was 4,23980,256. We split them up into, say, the 134 into 134. This will be 67 into 67. This will be 34 into 34. So, and this will be 17 into 17. So we split them up. Now why we split them up is because this torch.env sample need need this shape. So we split them up, we move this dimension here, we split them up, we moved this dimension, the 8 here, and 32 here, and make it this channel dimension for across the different things. Because why we do this is because this guy grid sample function require the grid sample, the value to be in this shape, and the grid sample to be in the range -1 to 1. So for the sampling locations we do that. So what it outputs is the corresponding for each level. So what happens is, for each level, so this we will get 32 300 4,2, right? For 4 levels are there, for each level we have this one. So for corresponding, when you do this for each of the query points, 300 query points, we are looking into uh, 4 points in this feature map. So we get 4 points there, and 300 for 300 query points we get 4 points. Similarly, for the next one also we will be looking like that. For 300 query points we get 4 points, and for 300 query points we get 4 points. For 300 query points we get 4 points. So like that we get 4 points each for each layer, and we stack them up, and we get 4. When we stack this much points up we get this one, then you flatten it, this one, this much. And now this was our attention weight. So we multiply for each of the query points, we multiply this attention weight, and this will give us the like multiplied one, and then we have to sum it up, right? So we multiply it, we get this one. uh, so after the multiplication we get this one, we sum over the last dimension, we get this one, then we rearrange and change to batch and head, and you get this one. So this is the output of first cross attention, the cross attention layer. So what we essentially did was, for 300 query points we look into 4 points in 4 feature map from the encoder, and finally we get the encoder output like this. And this is the final fully connected layer, which is similar to what find all the tensions. You have a two hidden layer, then a residual connection and layer norm in the output, and the output will be passed to by a another output projection layer. I'm mixing that here, so no, I'm not missing that here. Output projection layer is here, so it's there. Yep, that's fine. So after the encoder attention, we pass it to the output projection layer, and then the feed forward letter network, and find, yeah, this is correct. So this is very simple, rudimentary. So this will be that, and now we have to look into the final box prediction. The box prediction is actually very much similar to what is happening in Detr. So you have n number of classes, you have a bound class prediction head, and you have a box head. So predicting the number of 4 coordinates which are in the xy 0 to 1 constraint space. So one thing that you need to understand here is actually so here if you look into it, we have the reference point inverse sigmoid. So we had the reference point neural network predicting the reference point, and we actually sigmoided it so that it will be in 0 1 space, but the predictions is can be outside the 0 1 space, so we have to apply inverse sigmoid to it, and this will actually then we will have to add that to the box prediction head, and then we will, after the addition, we should take sigmoid and bring it back to the 0 1, because the targets are also in 0 1 for the scale, that is for the scale, and then you get, yeah. So this is one this is similar to what's happening in Detr. Only difference thing is this thing: you have a inverse sigmoid operation happening, and then you add it, and then you take the sigmoid again, because the prediction is not in the sigmoid space. This prediction logics are not in the sigmoid space. And for losses, the only difference in losses is in deformable data we have they use focal loss instead of cross entropy loss. In Detr they use cross entropy, here we use focal loss, and the GAU loss and LON loss for the bounding box remains the same. So that will be the final output. Next we will look into how the complexity of how much is deformable Detr saving.